So, welcome to section 8.2 on Lewis diagrams. You will want one of these. This is the lovely little PowerPoint package that goes with this section. You'll notice as well there's a lovely video by somebody who does this so much better than I do. Bozeman Science does Lewis diagrams. That's available from the menu as well. So I would encourage you, if you have any questions about Lewis diagrams, to go through both of these. But Lewis diagrams follows from what you already know about writing Bohr diagrams, and I'm going to let you decide which one you find more logical and easier to use, but you do need to know both of them. So just a quick little review. Bohr diagrams show how many electrons appear in each electron shell around an atom. You know that. These electrons in the outermost shell are given a special name called valence electrons. And these shells that we're talking about, they're actually three-dimensional spheres. Admittedly, on paper or on a screen, you're looking at a 2D circle. The fact is, these electrons are actually moving very, very, very rapidly through various probability spheres, and we just, for convenience, draw them the way we do. So, I will give you an example. If we draw a Bohr diagram for this element, you should be able to tell me what element that is just by looking at it. Why don't you grab your periodic table for a second, see if you can determine which element it is. And I will play with my pen for a second. That looks like fun. So, count the electrons. We got 2 in the first shell, 8 in the second, 8 in the third, total 18 protons. So in my way of thinking, I take that 18 protons and I look at my periodic table. 18 looks to me like that has to be argon, right? So it has 3 electron shells. I mean, look at all the information it's giving you just by looking at a Bohr diagram. It's telling you have 3 shells, therefore you know it's in period 3. You know it has 8 electrons in its outer or valence shell. There's other information as well. You should be able to draw the mass number. You should be able to write it in atomic notation. Mass number? What the heck is that? I'm going to write down mass number. Mass number. Mass number is equal to, do you remember? Number of protons plus number of neutrons. So in this particular case, we have just said that we have 18 protons. And if we look at argon, you're going to find that its atomic mass is 40. So, excuse me. In this particular case, we're going to have 18 plus 22 neutrons. How did I get 22 neutrons? I took 40 minus 18 equals 22. You would draw that in a special way. You would actually write symbol, argon, and you would write the mass number up there, 40, and then you would write the atomic number down here, 18. Of course, if this was an ion, you'd put some kind of a charge there, but argon hasn't lost electrons. For the actual chemical notation for argon, you would actually write argon dash 40. So that's what argon 40 means. This is the mass number. Okay, your turn. We are looking at another element from your periodic table. You should be able to look at that Bohr diagram and you should be able to tell us what element it is, what period it is in, how many valence electrons it has, and its mass number. And again, you should be able to draw it just like we did on the previous page, showing standard notation. An example, if the element was iron, which of course it isn't, with a mass number of 56, then we would write this in standard notation as iron 56. What other information should you be able to tell us? You should be able to tell us how many neutrons it has. So you might want to, at this point, stop the video and just take care of that. I'm going to move on because we're going to form some compounds. And again, you know about this stuff, but again, we're going to tie it into using Lewis diagrams and forming compounds. So when two atoms get close together, those electrons in their outer shell, their valence electrons, are going to interact. If the valence electrons can combine to form a low energy bond, you actually have a compound. Each atom in the compound attempts to have the stable number of valence electrons as the nearest noble gas. They want to achieve a octet, just like the noble gases. Of course, helium only has 2 electrons. That's its full outer shell. But the rest of them all have 8 electrons in their outer shell. They are the ones everything else is trying to be like. Metals are going to lose electrons. Non-metals are going to gain electrons in forming ionic bonds. Or, if you have non-metals, you can actually share electrons in what you know and love as covalent bonds. On the other hand, ionic bonds form when electrons are transferred from positive ions to negative ions. On the other hand, covalent bonds form when electrons are shared. There's the key word, between two nonmetals. So again, you have to be using your periodic table when working with this stuff to recognize which is which. Electrons are going to stay with their atom but overlap with other shells. Again, this is only true for obviously covalent bonds. With ionic bonds, those electrons are actually going to move. So, ionic bonds are formed between positive ions and negative ions. So usually this is a metal ion, something from the left side of the periodic table, with something that is a non-metal, something on the right-hand side. For example, lithium and oxygen form an ionic bond in the compound lithium oxide. That's what it would look like. Bohr diagram for lithium, Bohr diagram for oxygen. Lithium has 1 valence electron, oxygen has 1, 2, 3, 4, 5, 6 valence electrons. In order to form lithium oxide, you're going to have lithium donate 1 electron, another lithium donate another electron, and now oxygen is just so happy it's got a full outer shell of 8 electrons. And how you draw that in terms of a Lewis diagram is by actually showing once you've lost that electron, lithium has become a 1+ ion. Same with the other lithium atom. By losing that 1 electron from its valence shell, it's now Li+1. And oxygen, of course, is the receiver of those 2 electrons. It now has a full outer shell. If it gains 2 electrons, it has a charge of 2-. So make sure when you draw these ions, you're actually drawing square brackets around them and showing their charge. I'm going to leave some of these for you to do. We just did lithium oxide. I think you should try potassium chloride before we move on. Is it an ionic bond or is it covalent? Speaking of covalent, covalent bonds are, as you know, formed between 2 or more nonmetals. Here we have electrons being shared, something like hydrogen with fluorine. Fluorine can have a full octet in its valence shell simply by hydrogen sharing that 1 electron it has as well. So you would have something like that. So Lewis diagrams illustrate chemical bonding by showing only the atom's valence electrons and the chemical symbol. So that's a definition you probably should commit to memory. The Lewis diagram is simply showing how you undergo or have chemical bonding by showing the atom's valence electrons as well as its chemical symbol. So I'm going to show you a Bohr diagram and then the equivalent Lewis diagram. So this would be oxygen as a Bohr diagram. 2 electrons in the first shell, 6 electrons in the valence shell. As a Lewis diagram, you would simply show those 6 electrons evenly distributed around the oxygen core. There is an order to these. Again, you don't begin to pair up until you have 1 electron in the north, 1 electron in the east, 1 electron in the south, 1 electron in the west, and then you can begin to double up. It's kind of, well, it's called the bus rule. When you get on a bus and there's only 3 people on the bus, do you sit down beside somebody who's already sitting in a bench? Or do you fill up each bench with 1 person first? That's what you are doing here. You would make sure you sit here, sit here, sit here, sit here, and then begin to double up as you have to. So looking at another example, this would be sodium. Again, you're just taking the atomic number of sodium, tells you how many electrons it is. For that matter, the periodic table tells you how many electrons are in the valence shell. In the case of sodium, it's 1 electron. So for the Lewis diagram, you just draw 1 electron. You get to do one yourself. Fluorine. Again, draw both the Bohr diagram as well as the Lewis diagram. So there's rules here. Dots representing electrons in Lewis diagrams are placed around the element symbols at the points of the compass, as I mentioned. North, east, south, then west. 1 electron there, then 1 there, 1 there, 1 there, and then you begin to double up. Electron dots are placed singly until the 5th electron is reached, and then they are paired. So if you look at a periodic table just showing the valence electrons, you can get an incredible amount of information there. Notice group 18, the noble gases, full outer shells, 8 electrons, 8 electrons. Next door in the halogens, 17, group 17, these all have 7 electrons in their outer shell, 6 electrons in their outer shell, 5 electrons, 4 electrons. An easy way of doing that, of course, is just taking the group number and subtracting 10, and then you will get the number of valence electrons that you should distribute around it. Of course, that's not true on the left side of the periodic table. Group 1 tells you it has 1 valence electron. Group 2, 2 valence electrons, and so on. So just using that periodic table, you should be able to tell me, as on your little handout, how many valence electrons are in all group 18 elements. And again, this would differ between helium and the rest of the noble gases. How many valence electrons do all group 16 elements need in order to have a full valence shell? And you should be able to explain why oxygen forms ions with a 2+ charge. We're going to move on to Lewis diagrams of ions. Lewis diagrams obviously can be used to represent ions and ionic bonds. For positive ions, 1 electron dot is going to be removed from the valence shell for each positive charge. For negative ions, 1 electron dot is added. So electrons are negative, right? So if you're adding something negative, you're going to show an extra electron. If you're losing something negative, then you become positive. Once you have an ion, make sure you have square brackets placed around each of them. So, in the case of sodium chloride, good old table salt, you have a metal here losing its 1 valence electron to become a Na plus ion. Notice the square brackets, notice the +1 charge, or the plus charge. At the same time, chlorine is going to gain 1 electron and of course become a negative ion because electrons are negative. Again, notice the square brackets. By the way, you either have to designate that one is coming from another element here by drawing, say, an X, or by changing the color. So you could, of course, wonder if my pen still works, eh? In color, what were we using? Blue. You could, of course, draw this as square bracket Na plus and square bracket Cl minus with these lovely electrons around it, and then showing the 1 electron that has come from sodium as an X. So you have to distinguish that this has come from some other source. It's come from the sodium, right? Your turn. I just made a mess. Draw a Lewis diagram. Woo, that's fun. For an aluminum atom, okay, be careful now. No square brackets around an atom. You only have the square brackets around an ion. So aluminum, figure out what group it's in, and you know how many valence electrons it has. You should be able to do that. If you have a problem with some of these, talk to me in class and we will try to help you out. So Lewis diagrams of compounds. Lewis diagrams can be used to show ionic compounds such as magnesium oxide and barium bromide. How an ionic compound forms beryllium chloride is shown using Lewis diagrams. So magnesium oxide, magnesium's in group 2, so it's got 2 valence electrons. Those 2 valence electrons are lost as an ionic compound to form magnesium 2 plus ion, square brackets. Those 2 ions, 2 electrons, are donated to oxygen, so now oxygen has gone from 6 electrons to 8 to complete its octet, and of course by gaining 2 electrons it's 2 minus. And of course I've just said you have to designate that these 2 electrons have come from another source. We should probably have gone like this and used X's. Right. But the point is there, right? On the other hand, barium bromide, in this case, bromine has 7 electrons in its outer shell, and it really wants 8. Barium is in group 2, it's got 2 electrons it can give them, so the 2 electrons come from barium. Barium forms a 2 plus ion, and you show again the charge on bromine because bromine has gained an electron and barium has lost 2. So the last one, you are supposed to be able to draw how an ionic compound such as beryllium chloride might form. I would always start by drawing the Lewis diagram for each element. So beryllium, 2 valence electrons. Chlorine is a halogen, group 17, so it's got 7 valence electrons. Then you say to yourself, how can they form a stable compound? And the only way they can do that is if you have complete outer shells, valence shells, the octet rule, right? So in this case, beryllium can donate 1 electron to chlorine 1 and donate another electron to chlorine 2. And in so doing, you now have this ionic compound in square brackets where chlorine has gained an electron, chlorine has gained an electron, beryllium has lost 2 electrons. Piece of cake, right? Right. So, when you compare Lewis diagrams and Bohr diagrams, you should, after a while, begin to recognize the benefits and the difficulties with each, right? So in this case, water as a Bohr diagram, ammonia as a Bohr diagram, and methane as a Bohr diagram all become the following as Lewis diagrams. We've just taken, don't be afraid of these, what we will call a bonding pair. This HOH, H, is actually that equals that, right? So when you see a shared pair of electrons, these are simply sharing a covalent bond. So these happen to be what are called bonding pairs. This is a bonding pair. Bonding pair. Because those are the electrons that are being shared. Whereas these puppies, see these electrons? They're not involved in this bond formation at all. Same thing with these guys. These are called lone pairs. So again, lone pairs, bonding pair, bonding pair, bonding pair, bonding pair. So this is simply a covalent bond that really stands for a shared pair of electrons. It's basically this, right? Right. Your turn. Yes, you get to draw a Lewis diagram for sodium oxide, potassium chloride. You get to define a lone pair, and you get to define a bonding pair. Okay, I'm feeling sorry for you. Okay, potassium chloride. Maybe I'll leave a couple of these for you. But potassium chloride, I would draw potassium chloride as, okay, potassium is in group 1, so it's going to lose 1 electron. If it loses 1 electron, it becomes a +1 ion. Where's that electron going to go? It's going to go to chlorine, because chlorine has 1, 2, 3, 4, 5, 6, 7 electrons. But if it takes potassiums, it's now going to be a full octet. And we would say chlorine is -1. Ta-da! That's it, potassium chloride. I'll let you do wonderful things like sodium oxide yourself. We're just about done, people. Lewis diagrams of covalent bonds. Up to now, we've been looking at ionic bonds, and quite honestly, I would not use Lewis diagrams to show ionic bonding because it's rather straightforward that ions are just going from one metal ion to a nonmetal ion. Lewis diagrams I find far more useful in covalent bonding, where you're sharing electrons. The shared pairs of electrons are usually drawn as a straight line. So this line right here represents the pair of electrons shared by the atoms. It is just these guys right here. And again, always start with the Bohr diagram, not the Bohr diagram, the Lewis diagram of each individual atom, hydrogen, fluorine, and then you can show the sharing of electrons between hydrogen and fluorine with a straight bond. This would be called a bonding pair, right? Because those are the electrons involved in the covalent bond. On the other hand, all of these electrons, and again, it's not just the ones we're signifying up here, these, those are all lone pairs because they're not actually used in bonding. Right. Lewis diagrams can be very useful when drawing diatomic molecules. Diatomic molecules like oxygen contain 2 atoms per molecule. So if we draw oxygen as an individual atom, you'll see it has 7 electrons. The other one has 7 electrons. To be stable, they can form an octet by sharing 2 electrons in the middle. This, of course, is a double bond. You have 4 electrons. Instead of a single pair, you would actually share 2 pairs. It's called a double bond. And by the way, you can form triple bonds as well. Take organic chemistry, and you'll have all that kind of fun happening. So, your turn. Draw a Lewis diagram for the following diatomic molecule. All of the halogens tend to form diatomic molecules. Other diatomic molecules are hydrogen, H2, nitrogen, N2, oxygen, O2, chlorine, bromine, and iodine. If you ever see a chemical equation and they say that hydrogen reacts with something, nitrogen, oxygen, etc., make sure you write it as a molecule, H2, because to be most stable, they're actually going to form their diatomic molecules. So you might want to just memorize that because down the road, when you're writing chemical equations and you have to balance them, you can't balance a chemical equation properly unless you have the right formula for the elements in it.